right, everybody, welcome back. The goal for today's video is to introduce the concept of a vector, specifically for students who might not have already encountered vectors in pre-calculus, physics, or engineering. So what is a vector? The sort of physics perspective on vectors is that vectors are quantities that have a magnitude and a direction. A vector is a quantity that consists of a number referred to as the magnitude or the length of the vector, as well as an associated direction. So for a couple of example vector quantities, one of the quintessential vector quantities is the velocity of a moving object. When an object is moving and you're trying to understand its movement, one of the pieces of information that you would need to understand the object's movement is the speed at which the object is traveling. And the object's speed of movement is the magnitude, the number associated with the velocity vector. The direction associated with the velocity vector is the piece of data that tells you the direction in which the object is moving at that instant. Velocity is a quantity that has two pieces of data within it. A number, a magnitude that tells you how fast the object's moving, and a direction that tells you the direction along which the object is moving. Velocity is a vector quantity. Forces should also be understood as vector quantities. The number, the magnitude associated with a force vector is describing the strength or the intensity of the force. And the direction associated with a force vector tells you the direction along which the force is applied. And you need both of these pieces of data to really understand what a force will do to an object. Another vector quantity is what's known as displacement. And when we talk about the displacement vector, we're talking about a vector that represents straight line motion from an initial point, let's just call it A, to a terminal point, a final point, call it B. So a displacement from point A to point B might look like this, an arrow that takes us from the initial point to the terminal point. The magnitude is telling you the length of this green arrow that we've drawn. In other words, the distance that's separating your initial and your terminal point. And the direction associated with the displacement vector is the direction you have to travel to get from point A to point B. So in other words, the direction of this green arrow that we've drawn. The final quintessential vector quantity that I'll name in this list is acceleration. If you're dealing with an object that's moving in 2 or 3 dimensional space, for example, moving over time along a curved path like the one that I've drawn here, the acceleration experienced by this object is also a vector quantity. And that's coming from the fact that acceleration, just like it was in Calculus 1, can be understood as the rate of change of velocity. So if velocity is being understood as a vector quantity, then its rate of change will also be understood as a vector quantity. Now, the direction and the magnitude of acceleration actually convey quite a bit of meaning. And so we'll have a couple of lessons later on in this course where we study the magnitude and direction more carefully for the acceleration vector. So at this point in the course, when I refer to force, when I refer to velocity, when I refer to displacement, when I refer to acceleration, all of those quantities at this point in the course should be understood as vector quantities. From this point forward, all forces, velocities, displacements, and accelerations in the class will be treated as vector quantities. Now, the term scalar is used to refer to a quantity that's just a number and does not have an associated direction. So as opposed to a vector, which is a number and a direction, a scalar is just a number. So for examples of some physical quantities that are scalars and not vectors, we could talk, for example, about the cost of an object. The cost of something in the store could be communicated via a single number. For example, this item costs $120. The mass of an object can be communicated by just a single number. The mass of an object, for example, might be 8 kilograms. The age of an object or of a person, again, can be communicated just with a single number. You could say something like 31 years. Length and distance are also scalar quantities, and these can be conveyed just with a single number. For example, something like 4 meters. So you're going to hear me using these words often throughout the class, scalar and vector. Vector, a quantity that's number and direction. Scalar, a quantity that's just a number. Now, vectors can be represented graphically, and when we draw a picture that represents a vector, we draw the vector as an arrow. The same way that we drew the displacement from point A to point B as an arrow in this example. When you represent a vector graphically as an arrow, the direction of the arrow is what stores the direction of the vector. And the length of the arrow is what stores the magnitude slash the length of the vector. To give you some examples, let's go ahead and draw some vectors representing each of the following physical quantities. So for example, a displacement vector from an initial point -1, 2 to a terminal point 3, -5. So if I mark this initial and terminal point on the xy plane, the first one is here at -1, 2. This is our initial location. And the terminal point is over here at +3, -5. So this is our terminal location. And then the displacement vector that takes me from this point A to this point B would be the arrow, would be drawn as an arrow that directly connects us from point A to point B. So this arrow points in the correct direction. The arrow's direction takes us from point A to point B, and the length of the arrow conveys the magnitude of the displacement. The length of the arrow is equal to the distance between these 2 points. For a secondary example, suppose that someone wants me to draw an arrow representing a certain velocity. A velocity vector for an object that's in the xy plane, moving to the left at a speed of 30 meters per second. Now, when we draw vectors, we can draw our vector at any position that is convenient. As long as the magnitude and the direction of the vector is correct, the location, the position of that vector doesn't matter at all. So it's common to draw vectors starting from the origin, unless you have some specific reason to draw the vector from some other starting location, like we did in this displacement example. Now, for this vector starting at the origin, I'm going to extend the vector to the left because I'm told that the object is moving to the left and velocity points in the direction that the object is moving. I'm also going to draw this vector with a length of 30 units. The reason I'm drawing it with a length of 30 units is because I'm told that the object is moving with a speed of 30 meters per second. And I remember that the magnitude of velocity, the length of velocity, is representing the speed of the object's movement. So this pink vector stretching 30 units to the left would be a drawing of the velocity vector for this object, moving to the left with a speed of 30 meters per second. Let's go ahead and draw a vector representing standard gravitational force, standard Earth gravity, acting on an object with a mass of 10 kilograms, situated in three-dimensional space. So here is a copy of three-dimensional space. And I'm going to draw the gravitational force vector within this space, remembering that the positive x-axis traditionally points forward, the positive y-axis traditionally points to the right, and the positive z-axis traditionally points up when in math we draw 3D space. Now, gravitational force is going to act straight down. So my gravitational force vector will be pointing in the negative z direction. Now I just need to figure out how long is this vector? What is the length of this vector? In other words, what is the magnitude or what is the intensity of this gravitational force? I can use a formula from physics, which says that the magnitude of gravitational force is equal to the product of the object's mass, which I'll call m, and a constant called g. M is the object's mass in kilograms, and g is a constant usually taken to be around 9.8 meters per second squared in standard Earth conditions. G is going to be a little bit smaller if you're at a very high altitude, and G might be a totally different value altogether if you're not on planet Earth, if you're on the moon, or if you're on Venus or something. But for standard Earth conditions, G can be taken to be, roughly speaking, 9.8 in its value. So let's use this standard Earth value for G, and let's use the object's mass to determine how strong our gravitational force vector will be. Our mass, we're told, is 10 kilograms, so let's plug that in for the value of m. And g we're taking to be the constant 9.8. So the magnitude of gravitational force is 98 units. And since the magnitude of the force is what's stored in the length of the vector, force vector is going to point 98 units straight down, 98 units in the negative z direction. So this would be the drawing of the gravitational force vector acting on this object in standard Earth conditions in 3D space. Finally, let's go ahead and draw a picture of a force of friction, a resisting force. A resisting force that has a magnitude of 5 newtons that's acting on an object that's moving straight down in the xy plane. So in the xy plane, my object is moving down, but down is not going to be the direction of the friction force vector. Friction always acts in the opposite direction of movement. It acts to resist the object's movement. So if the object is moving straight down, friction force is going to act straight up, opposite the direction of movement. And then the intensity of this force, the magnitude of this force, we are told is 5 Newton. So 5 would be the length of this friction force vector that we've drawn. So this is how vectors are drawn. Vectors are drawn as arrows, and the direction of the arrow corresponds to the direction of the vector. The length of the arrow corresponds to the magnitude of the vector. So for example, if you're dealing with velocity vectors, longer vectors correspond to faster movement. Shorter vectors correspond to slower movement. If you're dealing with a force vector, longer vectors represent more intense forces. Shorter vectors represent weaker forces. For velocity vectors, longer vector means faster movement. Shorter vector means slower movement. And for force vectors, if you see a long vector, that communicates a strong or intense force. And if you see a shorter vector, that represents a relatively weak force. Now that we've talked about how to represent vectors graphically in pictures, let's talk about the symbolic notation that's used for vectors. Now, depending on whether you're in math class or in physics class, you can see vectors represented in a couple of different ways. One way that you'll see vectors represented, particularly in Calculus 3 and 4, is by using this angle bracket notation. Angle bracket, for example, 3, comma, minus 2. The physics notation for this exact same vector looks like this. 3 times a quantity called I hat minus 2 times a quantity called j hat. These two are two different notations, one more common in math, the other more common in physics, both representing the exact same vector. So what is the vector that is represented by this symbolic notation? If I'm given a vector 3 comma minus 2, here is how I should understand it. To draw this vector, you start at the tail of the arrow which we remember can theoretically be positioned anywhere in space. We're going to travel 3 units in the positive x direction. And we're going to travel minus 2 units in the y direction. And that movement will give us the location of the arrowhead. Let me show you what I mean. So one option is to draw the vector with the tail positioned at the origin. As mentioned earlier, this is a pretty standard position for a vector unless you have some good reason to position the vector somewhere else. If the arrow's tail is located at the origin, then to find the arrow head, I would move 3 units along positive x and 2 units along negative y. And the arrow head would be located right down here in the fourth quadrant. So this vector, 3, -2 in the angle brackets, would be the vector stretching 3 units in the x direction and 2 units in the negative y direction. This guy would be a representation of the vector 3, -2. Now you could position that arrow tail somewhere else. For example, if I decided to position my arrow tail over here for whatever reason, then I could draw the vector by just going from that point 1, 2, 3 units along positive x, 1, 2 units along negative y, and from that position the arrowhead would be, roughly speaking, right around here. So this would be another drawing, another totally valid drawing of the same vector 3, -2. It's got the exact same length and the exact same direction. It's just positioned in a slightly different place. So that means that it's the exact same vector. Similarly, if you position your vector somewhere over here, the same kind of rule applies. Go 3 to the right and go 2 down to reach the arrowhead from that initial position. This is another drawing of that same vector 3, -2. Now, three-dimensional vectors can be represented similarly. In math notation, you might see, for example, something like 3, -2, 5, representing a three-dimensional vector. In physics, you might see something like 3i hat minus 2j hat plus 5k hat, representing this vector. And this is just telling you wherever you put the tail of your arrow, then to find the head of this arrow, we go 3 units along x, we go 2 units along y in the negative direction, and we go 5 units along z. It can be quite difficult to draw three-dimensional vectors by hand in a way that makes sense. So when I'm drawing three-dimensional vectors, I will usually use some kind of website to help me draw the picture more accurately. For example, a website like GeoGebra 3D, or another nice one for vectors is Math 3D. So here I am, for example, on Math 3D, and you can see that they've given us a copy of three-dimensional space here. I'm going to go over to the left-hand side and add an object, and I'm going to add a vector object. And it's given me sort of an example vector with the syntax that it wants to use. This software wants to use the syntax of square brackets for the vector. Okay. Let me go ahead and type in the vector that we have in this example, which is 3, -2, and 5. So 3, -2, and 5. So what we see is that they have defaulted their vector so that its tail is at the origin, pretty standard default location for a vector. And then to reach the arrowhead of the vector, from the origin, they're going 3 units in the positive x direction, 3 units along positive x. They're also going 2 units along negative y, 2 units along negative y, and they're also going 5 units vertically, 5 units along positive z. So that is how three-dimensional vectors are drawn, but it can be quite difficult to draw them accurately just by hand. Now, a bit of terminology. If you're talking about a vector, there are special names for these numbers in the angle brackets. For example, this number 3 in the lead that tells you how far to move in the x direction is referred to as the vector's x component. And this number -2 in the second position is called the vector's y component. And then if you're dealing with a three-dimensional vector, you might also have a z component. For example, here the z component is 5. So when you refer to the components of a vector, the x component, the y component, and maybe the z component, then you're talking about the entries of the vector in these angle brackets, the numbers 3, -2, and perhaps 5. So let's go ahead and find the vector representing each of the following quantities, the same physical quantities that we drew above, but this time we're actually going to go ahead and find the components of these vectors, the x component, the y component, and possibly the z component, so that we can write the vector symbolically. Now, what I see is that this vector is requiring me to move from x equals -1 to x equals 3. So the x component is 1, 2, 3, 4 units in the positive x direction. In other words, the x component can be found by taking the terminal x and finding the difference between that and the initial x. We have an x component here of 4 units. You have to go 4 units in the positive x direction to get from the arrow tail to the arrow head. To get from the arrow tail to the arrow head, I have to move down in the y direction. I have to move down 1, 2, 3, 4, 5, 6, 7 units. I have to move down 7 units. And again, that -7 can be found by subtracting the terminal points y and the initial points y. If I take the final y value, -5, and I look at the difference between that and my initial y value, 2, the difference between them is that value of -7. So by subtracting the 2 points in the order terminal minus initial, I can get the components of this displacement vector, 4 and -7. So in math notation, I would write it like this, angle bracket 4 -7. If I want to use physics notation, I could write it like this, 4i hat -7j hat. Let's find the components of the velocity vector from part B. The velocity vector for this object that was moving directly to the left at the speed of 30 meters per second. So what we see is that if you position, for example, the tail at the origin, to reach the arrowhead, I would have to move 30 units in the negative x direction. So the x component of this vector would be -30. I have to go 30 units in the negative x direction to reach the arrowhead. The y component of this two-dimensional vector is just 0 because there's no difference in the y values between the initial position and the final position. I did not move any units either up or down as I traveled along this vector. So the y component here is 0. So that means as I write this vector, I can write it in angle bracket notation as negative 30, 0, or I can write it in physics notation as negative 30i plus 0j, which can be simplified to just negative 30i. So this is the symbolic notation for this velocity vector, 30 units in the negative x direction. What about that 3D vector representing this gravitational force? In this three-dimensional vector, the force was pointing 98 units straight down in the negative z direction. So that means that our z component is negative 98. Meanwhile, nothing is really happening in either the x direction or the y direction, so the x component can be taken as 0, and the y component is also 0. So what this means is the symbolic notation for this gravitational force in math notation is 0, 0, negative 98. In physics notation, it would be 0 I hat, 0 j hat, minus 98 k hat, which could be simplified to negative 98 k hat. And finally, that friction force from earlier. The friction force from earlier in two-dimensional space was pointing 5 units straight up. As a result, it's going to have an x component of 0 and a positive y component of 5 units. So the symbolic notation for this vector is going to be 0, comma, positive 5 in math notation, or in physics notation, 0 I hat plus 5j hat, which could equivalently be written as just 5j hat. A word of warning, something that I see from a lot of students as they first get started on this work is taking the two notations for vectors, the math notation and the physics notation, and kind of mixing them together. But you have to commit to either the math notation or the physics notation. So you're not, for example, allowed to write something like 3I hat, comma, 2j hat. The angle bracket notation is exclusive and is not to be used with I and j. Another thing that I see from students that is incorrect notation is something like angle bracket 3I hat plus 2j hat. This is not a thing. This is a syntax error. This is incorrectly expressed. So you don't want to be using these two different notations at the same time. Commit to a single type of notation. Either just the angle brackets with the components between, or just the I hat, j hat with no angle brackets. But you should not be writing a vector that has both the angle bracket notation and the i's and j's. That is a syntax error. Okay, that concludes this video. In this video, we talked about vector quantities, which are quantities that consist of two pieces of data, a magnitude and a direction. For example, velocities and forces are best understood as vector quantities. When you draw a vector, vectors are drawn as arrows, where the direction of the arrow is the direction of the vector, and the length of the arrow is the magnitude of the vector. And when you draw vectors, their actual position doesn't matter. It's traditional to draw them starting from the origin, but sometimes it's more meaningful or more appropriate to draw them from other starting locations. In addition to being drawn as arrows, a vector can be represented symbolically using either angle bracket notation or using the physics IJK notation. These numbers are called the components of the vector, and the individual components are telling you how the vector is extending in the x direction, the y direction, and if you have one, the z direction. For example, 3 minus 2 extends 3 units in the x direction, positive, and 2 units in the y direction, negative.